So we're going to have a look at analysing data sets. So we're going to have a look just at the different types of raw data that we can be given and the different ways that we can analyse this. So the key skill for anyone working with statistics is to be able to choose the correct graph calculation or hypothesis test to help explain the data to the public and their target audience. Because the whole point of statistics is that we are not just given a big set of data and that's it. We have to find out information about it, and then we have to decide the best way to present that to people so that they can understand what we have found. So the first thing is if we have a single sample data list. So it could look like this, it could just be a set of numbers. This is one list of data from a single sample. It's only one variable, and it is the simplest solution. This can be presented in a table or a list. So there's possible things that we could be asked to calculate. So we could look at the mean, the mode, the median, the range, the interquartile range, standard deviation, the outliers, the skew. Possible graphs that we could draw with this data would be box plots. And if we're given this type of data and then we're thinking about what type of hypothesis test we could do a normal hypothesis test. If we've been given the population mean of something and we're trying to compare, is this data higher, lower, different? We could do a single sample sign test if we're given the population median, and we could do a Wilcoxon signed rank test if we're given the median or the mean and we're told that the data is symmetrically distributed. So then the second lot of data that we could have would be if we had a single sample of data but in a frequency table, and we can find most of these things are the same. So again, mean, mode, median, range, interquartile range, standard deviation, outliers. Graphs this time could include a box plot, or we could have a bar chart, since we've got sort of categories that we've got there with our variables because we've got our frequencies. And again, we could be asked to test for normal distribution, single sample sign test, or the Wilcoxon rank sign test with the same caveats as what we were talking about in the previous part. So then we could be given a single sample of data but with grouped frequencies. So here you can see that we've got our intervals, and here we would have our frequencies. So this is usually done when we have continuous data or if we have decimal places. It's unlikely to represent values. The data can be grouped. It's like this. So we've got possible calculations could be an estimate for the mean, because we would have to use the midpoint of the interval to help us to estimate that. So it's not going to be the exact mean, it's going to be an estimate for it. The modal class, picking out the one with the highest frequency. We could use interpolation to find the median, the upper quartile and the lower quartile to find the interquartile range. We could assume our endpoints are at the furthest points to find the maximum range, or at the minimum points to find the minimum range. We could find an estimate for the standard deviation. Again, that would only be an estimate because we'd have to use the midpoints of the intervals to be able to calculate that. We could estimate for outliers, so we could tell if we had some data that was outliers, or if it was possible that we did have some outliers. If we were told that an outlier was going to be 1.5 times the interquartile range added onto the upper quartile, and that ended up being less than at the end of our intervals, then that means that we could have some outliers there. And we can have a look at skew as well, because we can have a look at the distribution of the frequencies to help us to determine if our data is skewed. Now from this we could draw a box plot, a histogram, or a cumulative frequency, and we could still be asked to do the normal hypothesis test, but we wouldn't be asked to do a sign test or a Wilcoxon rank sign test with this, because we can no longer say either what the size of the difference is or what the sign of the difference is, because we don't know the actual values of data. We only know what interval they fall in, but we can find an estimate for the mean of this data and then compare that to the mean of our population. So we could be given single sample data that has a time frame, such as this. So here you can see that we've got years and we've got quarters, and time frames can be over any length of time. It could be months, years, quarters, could even be hours and minutes, things like that. So possible things that we could find, well, because we do still have a list of numbers, we could find the mean, mode, median range, interquartile range, standard deviation, outliers, skew. It's not really practical or insightful, some of these, okay? Yes, the mean would help a little bit, but the whole point in having the time data is to see how things are changing over time. So something that's probably going to be more useful is making a time series graph and then looking and commenting on the peaks and thoughts about what's happened there, if we've got any seasonal or cyclic variation, if we've got any long-term trends of the data, or if we've got any anomalous results that we can see there. There's nothing particular that we would test with data that has a time factor to it, just because it's usually that we are looking at what has happened over that time frame rather than the average over that time frame. So then we have, if we have multiple samples of data and a time frame, then again we could find that same information, but this time we would make a comparative time series graph. So we could still make the same comments as before about the peaks, thoughts of why those peaks might happen, if we have seasonal cycles or variations, but also we could talk about comparisons. So we could talk about, are they matching? Is one always larger than the other? Is it opposite over long terms? And if the group is the sum to 100%, then we could make proportional pie charts from the first. So here for the data that we've got here, we could do it from the first. We could do it from January and June, and we could compare how group A to C has changed in its distribution from January to June. So we could see how they have changed. So we could have two single samples of data, okay, something like this where we have a before and after. We could find the mean, mode, median range, interquartile range, standard deviation, outlier, skew, so that we can compare the average and spread before and after. We could draw a dual bar chart. We could do two box plots to compare them with each other. And in terms of hypothesis test, this would be ideal for something like a sign test or a Wilcoxon signed rank test, because we have the same variable here. The other thing that we could have is bivariate data. So here we could have, so we have one person and we know two different things about them. Again, we could find the mean and the standard deviation, but it's more likely that we'd be looking at things like regression line, residuals, outliers. Graphs that we draw would be scatter diagram with x being variable 1 and y being variable 2, and we draw the line of best fit on there. And we might go as far as to have a look at PMCC or SRCC to be able to help us to tell if we have got a correlation between our variables. Or we could have two completely separate samples of data like this, where it's not paired data, it's just two samples of data, which means that we could, again, have a look at our averages, mean, mode, median range, interquartile range, standard deviation, outlier, skew, for the two sets to be able to compare them with each other. We could have a double box plot, so again, having a box plot for each one of those, and we could do Wilcoxon rank sum. So that's the difference between this one and the previous one that we had a look at. If I just go back to that one just before the bivariate data. So this here is where we have paired data. So we have the same person doing before and after. Here we have two samples of data, one being done by some people and the second one may be being done by completely different people. So this can help in terms of if you have an experiment which has a high dropout rate where people might do the first one and then drop out and don't do the second one, then this can really help, because then we're not having to rely on them continuing. It also helps if you're testing two different things, but you're wanting it to be, if you're testing the same skill, but you're not wanting that person to get better at that skill because they've seen the test before. So you might want different people to do it then, rather than the same person doing it twice, because you don't know whether they're only doing better at it because they've seen it previously. So we can identify the difference between paired data and bivariate data. The main thing is about the context of the wording around the questions. So having a look at the table doesn't help that much. Here, I could have either bivariate data or I could have paired data. Okay, it's hard to tell by having a look at it. So if I had something like having a look at the correlation between the two scores, then I know that I'm treating it as bivariate data. Whereas if I was having a look for a change between test 1 and test 2, then I'm treating it as paired data, not bivariate data, and then I can do a sign test or a Wilcoxon rank sign test on that. So paired data is usually about to see if the student has done better in test 2 than test 1. In this case, we do the Wilcoxon sign rank test if it's suitable, meaning that we have symmetrical population. If not, we do the sign test, especially if there is some kind of intervention that has gone on between the two tests to see if it's improved. Whereas it would be treated as bivariate data if we're having a correlation. If we're having a look at the correlation between test 1 and test 2, in which case we'd have to think of whether our data was bivariately normally distributed in order to decide on whether we were doing PMCC or SRCC, which one of those would be more suitable. So the final part of the decision-making process is to decide on analysing the data, is deciding which hypothesis test to use. This can be quite difficult. We've got quite a lot of hypothesis tests now at the end of AS. I'm going to learn even more of them in A2, and it does help to have a little bit of a thinking system going on. So in some situations, the hypothesis test to undercover is not stated and you must make a decision, and it's leaning more and more towards that now. So here are some questions that you may want to ask yourself. So does it tell you the name? If so, do that one. If it doesn't tell you the name, then does it specify the underlying populations? Does it say that it's normally distributed? Does it say it's non-parametric? Does it say it's symmetrically distributed? Does it state the type of test? So non-parametric, okay, so that's looking at our Wilcoxon rank sign, Wilcoxon rank sum and sign test. Does it state what is the best tested, what is being tested for? So does it mention words like correlation, association, mean, median, things like that? And we have given you here some flow diagrams to show how that thinking process can work. So here we have parametric tests. Okay, so that's talking about where we know the underlying distribution, and you can see that then that leads to, if n is large, then we're doing a central limit theorem or normal hypothesis test. If no, then it ends up going into A2. That's why it says out of the scope of the course, because that would be in the A2 part, not the AS part. You can see that we lead down to PMCC there and normal hypothesis testing here. And again, t-test here, which is now in the A2. For the non-parametric one, we can see that, again, we're having to think of, do we have a contingency table? Well, yes, then it's chi-squared. So remember, contingency table is a two-way table. So if yes, we have a contingency table, we could do a chi-squared test. If no, then we could do Spearman's rank. And if we're looking at the median, okay, then we could be having a look at the sign test, or we could have a look at the Wilcoxon rank sign test. We just have to decide if it is paired or if it's two sample, and also if it's symmetrically distributed, to decide on whether the sign test would be suitable. And then we could also think about if it's independent samples, then again we'll get into the Wilcoxon sum rank test. So that's the end of that part there. I hope that, I know it's been a lot of me talking, but I hope that it helps you to think a little bit more about how, just by looking at the set of data that you have, that you can have a think about what you're going to be expected to do with it, as well as having a think about what kind of hypothesis tests and graphs are suitable for different types of data, because more and more now they might not ask you to do the graphs, but they might give you a set of data and say, you know, Josh wants you to do a presentation using this data that's suitable for the board of directors, and then if you say a scatter diagram but you've got a single sample of data, that's not going to be suitable enough. Okay, so hopefully this has helped you a little bit. Thank you very much for watching, and I'll see you later.